everyone to this Forestry Commission England funded Building from England's Woodlands project, which is led by the New Model Institute for Technology and Engineering, which I'm the director for the Centre for Advanced Timber Technologies at. It's also partnering with Edinburgh Napier University, where I'm also a professor, and work with my colleagues Dan, etc., who will be presenting in the first session, as well as dRMM architects who are here today, and ecosystems technologies. We've got quite a tight packed agenda, so I'm really just going to hand it over to Dan, and then what I'll be doing during the course of the day is just popping back up to help move the questions along, and then point you out for the coffee and tea breaks, and then bring you back in. And at the end of today, we'll have the Transforming Timber launch, which will beam in live for you all to see and participate in, and then we'll guide you, for those that want to join us, for networking drinks afterwards. But without further ado, I'll really hand over to Dan to kick us off. Okay, so thank you.
Thanks, Robert, and thanks everyone for coming. We've got a real mixed audience here, with people who are already pretty knowledgeable about hardwoods, have been using them, and some people who probably don't know that much about timber engineering who've come along to find out. So the purpose of this first session really is to do some basics to get everyone up to speed. I will be telling some of you things that you definitely already know, but the idea is that we all know what we mean by certain words, and we can have a good conversation when we come into the wood products stuff later on. But before I start talking about wood properties, I just wanted to say a few things about the project itself. So it's called Building from England's Woodlands, and it's funded by the Forestry Commission. And its aim is to enhance the use of the forest resource that we have in England, and you'll be finding out a bit later about in what ways we're not making full advantage of that right now. Our prime target's the built environment, so that's timber in construction, not necessarily the structural parts, could be the non-structural parts too, but essentially in buildings, because we have a huge material need for materials for buildings. And we're trying to demonstrate what's possible and what's scalable, and to gather a bit of information that will be helpful for informing future forest strategies. And so we're trying to derive scalable solutions to do with compatibility with modern methods of construction, but we're also interested in the skills shortage, so education and outreach, and thinking about scalable ways of doing that education and outreach too. So as I say, this is funded by the Construction Innovation Fund. It's a 3-year project, and we're about a year into it. Speaking today, you've already heard from Robert Hairstands from NMITE and Edinburgh Napier University, and myself from Edinburgh Napier University. You'll also be hearing today also from Finn, from dRMM, my colleague Marlene from Edinburgh Napier University, and Wojciech, and Paula, who's at least in 3 different universities at some point, but Edinburgh Napier University and NMITE in Hereford. So we've got 5 work packages, and 4 of those are to do with actually doing research work. And today we're going to be touching on first work package 2, which is about wood property characterization, so basic information about the wood itself. And then we're going to move on to what we're calling optimized engineering timber products, but basically what can we do with that wood that's useful. Later on in the project, we'll start thinking about pilot manufacture and prototype testing, but we're not there yet, so we won't be saying too much about that today. And of course, this is a kind of outreach and education thing that we're testing out. So what are the aims of today? Well, they're to put the project into context for a general audience. As I say, we've got some people here who are very knowledgeable, perhaps know more about certain topics than we do. But we've also got some people here who don't know that much about timber engineering and have come to learn the basics, so we're going to start with that. And we're going to summarize what we've done in that first year, and we're going to hopefully have a bit of space for questions and answers, and that'll be both ways. So as well as you asking us questions and us giving the answers, we want an opportunity as well for us to ask you questions and for you to give us information. And later on, we're going to launch the Transforming Timber platform, but I'm sure Robert will tell you more about that. So this is what you're in for today. We're going to start with the timber properties, then we're going to have a 15-minute break, then we'll go into the wood products, then another 15-minute break, and then it will be the launch event for Transforming Timber. And then we're going to go for a drink if you want. Now, if you want to start thinking about the drink, this is where you'll need to head. So you go on to Tottenham Court Road, head north almost up to the tube station, Warren Street, but not quite that far, and it's the Court. Just follow, follow Kirsty. I'll bring it up at the end when we're ready to haul out. Right, so wood properties. Basically, this work package is trying to answer these questions. So what species have potential? What are their properties? And what is their best route for strength grading? Strength grading being the process that you have to go to if you want to use it for structural timber, because you have to guarantee certain properties that make the building safe. And how do we do this for the new species? And new might be a very familiar species, might be native to the country, might have been here for thousands of years, but it might be new to the wood chain. So we don't have a better word than new. And are the existing routes still fit for purpose for some of the species that we can theoretically put into buildings right now? So I'm going to start with just talking about words as us engineers and wood scientists use them, just so that you know what we mean when we use these words. The first one is strength. And strength is describing how much force, how much load something can take before it breaks. So this is a very important property from a building safety point of view, because if we get the strength wrong, the building collapses, people might die. Definitely you get sued. So it's an important property. Then we have stiffness, and stiffness is describing how much something moves for a particular load. So that's the deflection of a beam in your floor, or the buckling of a column, or the vibration of a floor. Something that feels bouncy, well, because it has low stiffness. And that's a less serious problem. That's what we call a serviceability failure. So it's a building that's not fit for use. People might not like it, but no one dies. But you still might get sued. And then we've got density. Now, density is, as it sounds, describing the amount of mass per unit volume. But density is used for a proxy for things like fire performance and fasteners. And also, of course, the weight of the materials in a building. So density in some ways, in some part of engineering design, is a lot like strength, because it's to do with the serious problems that we might get wrong, because it's about connections and it's about fire performance. Now, hardness. Hardness specifically means how easy it is to push something into the wood. Like, can you push your fingernail into it? Can you push a steel ball into it? So it's an important property for things like flooring, when you don't want the flooring to get marked by high heels and things like that. But it can also be a problem for manufacturing. If timber is too hard, it becomes difficult to put screws and so on in it. And then we've got durability, and durability can describe a number of different things. Often we're talking about natural durability against things like fungi and insects that might want to eat the wood. But we also might use the word durability to talk about things like whether a piece of wood on the cladding of a building will change color over time. So it's something to do with a degradation of properties over time by some natural effects. And there really is no correspondence between something being strong and something being durable. It's a separate property. So some other words to describe the various actions that we might have on a member. Tension is the pulling action. Compression is the pushing action. And I'm showing in these animations the direction along the grain, but often in timber, the things that we need to worry about are actually perpendicular to the grain. And I'll show you what that means in a moment. Bending is, as it sounds, something bending. But then we've got shear, and shear is a square going in a diamond shape, essentially. That's what's going on there. And torsion, which is twisting. So when I talk about strength for wood, there are many types of strength, because each of these different actions has a strength, and there's a different strength along the grain perpendicular to the grain. So there's a lot in there. That's just touching on it. We will use a lot of other words to mean the same things. So we might use MOR instead of strength, and we might say MOE, or modulus of elasticity, instead of stiffness. We'll try not to, but that might happen. So that's basically what we mean. A little bit about wood anatomy. So this is a block of oak, and you can see on the diagram here that we've got, can I bring up the pointer? we have the bark, and underneath the bark is the cambium, which is the growth layer. And these kinds of trees are growing taller by mechanism of growing outwards. So each year they're growing a new growth ring. So if you mark your name on a tree, this kind of tree, it won't go up in the air because the tree's basically growing outwards. So unlike a bamboo or a palm, which does go up in the air. And because of that growth, you end up with these annual rings. Now, these annual rings may or may not be visible. So what you learnt in school about an annual ring being a year of growth is basically true, but sometimes it's very difficult to see those annual rings. So in species like Douglas fir, they're very, very obvious. You can hardly miss them. But in a species like sycamore or birch, they're practically indiscernible to the naked eye. So, what is the difference between hardwoods and softwoods? Well, in the English language, we generally are talking about whether they're a kind of tree that has flowers or a kind of tree that reproduces with cones. So hardwoods are the trees like oak and ash that have broad leaves and flowers, or sometimes the flowers are very small. They don't look like flowers that you would take home, but they have flowers. And then we've got the softwoods, which are the pine, the fir, those kind of trees that have needles and cones. Of course, in engineering and wood products, we don't really care that much about how the trees have sex. So we're mostly concerned about what's different about these materials, what's different about stuff that comes from a hardwood and stuff that comes from a softwood. In other languages, by the way, hardwood and softwood does describe whether it's dense and hard. In English, we're not using hardwood and softwood in that way. Hardwoods are, generally speaking, harder than softwoods, but it's not a hard and fast rule. You have hardwoods like balsa, which are very soft, and softwoods like yew, which are very hard. The differences are really to do with the microstructure and how they grow. These two, the micro CT scans here are a different scale, so I really need to zoom in a bit further onto the softwood to see what's really going on there. Now we have, in the hardwoods, vessels or pores. They're big canals for the sap in the tree. In the softwoods, we don't have those. We just have general purpose cells which are doing the sap conductivity and providing the strength. So softwoods, generally speaking, are all very similar, independent of the species, because they only have this really one-purpose cell to do all that work, whereas hardwoods can be much more variable because they can have different arrangements of vessels and different shapes and sizes of vessels. And also, hardwoods and softwoods then have different ranges of density. So a hardwood can be very lightweight and it can be very, very heavy because of this difference in cell structure. So the other thing that I wanted to show these micro CT scans for is to show you, to help you understand why the wood would have dramatically different properties in the different directions. So in the longitudinal direction, up and down in the living tree, that's where it's most strong, because that's the direction of the load in the living tree, and that's along in the direction of the cells. But the direction that wood is particularly weak in is the direction perpendicular to the grain, where it, in this direction, where it's quite easy to pull apart the thin walls of the cells because there's less wood holding the wood together, if that makes sense. So, as I say, one of the reasons that hardwoods can be much more variable is the variation in the vessels. If you're interested in Wood ID, I do recommend these videos by Mississippi State University. I'm just showing you there to show you the variation that you can find in hardwoods. And of course, one of the things that we would do with Wood ID is to look how it appears, its color, its smell, its feeling. And those are all unique to different species, and it's one of the less tangible aspects of wood properties. One of the reasons that we might prefer one species over another is just maybe we like the appeal of it, and an appeal that we can't really measure in any scientific way. So hardwoods and softwoods, they also tend to come from differently shaped trees. Stereotypically, a softwood would be a tall tree, thin, relatively straight, with relatively small branches, and often those branches would be at certain heights in the tree. We call them nodes, and between those there would be relatively knot-free wood. Hardwoods, stereotypically, would be a little bit shorter, larger trunks perhaps, but certainly bigger branches and less organized. Which means that we can get long logs, typically from softwoods. We can get softwoods will give us also more uniform logs, whereas hardwoods will give us much more variation in the log shape and size. No hard and fast rule, of course, because we can also have trees, hardwoods trees shaped more like this, poplar, for example. It's kind of to do with not just the species, but the forest management as well. So we'll end up then with different types of logs. So the softwood industry is kind of set up to mass produce timber from a relatively uniform stock, whereas if we're talking about hardwoods, that certainly as they are now, it's a much more varied stock, fewer logs, a range of sizes, a range of lengths, and probably a bigger mixture of species as well. And there would typically be different cutting patterns to do with the technology of the mills that would be processing this. So hardwoods would tend to be cut through and through, so you'd end up with waney-edged boards, whereas softwoods would be processed in a big complicated mill that could cut it up directly into rectangles. So different technology typically for the hardwoods and the softwoods. It's not really to do with whether it's hardwood or softwood, it's just the markets that have developed up around those resources. And there are mills that sit in the middle that would process hardwoods and softwoods, maybe on a different line, maybe on the same line. This is Grosvenor Woodworks. I'm showing that building because that's made of C16+, which is one of the new grades that we invented, and I'll explain a little bit more about that in a moment. So hardwoods and softwoods, the other thing is the way that you work with them and the other processes that are involved, like planing, cutting, drying. And hardwoods typically would be air-dried, and softwoods typically would be kiln-dried. But again, it's not a hard and fast rule. This picture here is actually a hardwood kiln operation in the Netherlands. Other big difference between hardwoods and softwoods is the knots. Knots are where the branches were. In softwoods, we would tend to find lots of small knots, all kind of similar size to do with the way that those trees branch. Whereas in a hardwood, we might find a very big knot because hardwood trees can have big branches. The other thing that's different is that dense hardwood, or a dense softwood actually, the density of the knot and the density of the clear wood would be quite similar. Whereas typically in a softwood, they're very different. A knot is much denser than the rest of the wood, which means you can detect it with X-rays and other techniques. So differences to do with the kind of features that you see in the knot, in the wood as well. And, of course, log form is really important. And if you are actually managing your forest for production as your primary aim, you would be aiming for a log that is long and thin. This is American red oak from Lincolnshire, a nice log for sawing. Now, I will not rant because I don't have that much time, but one of the things that's often said about UK timber is that it grows too fast and therefore has low density and low strength. I will not get into the long grass there, but that's all wrong. There is no correlation really between ring width and tree growth rate. That does sound like it doesn't make sense, but trust me, it does. Go and look at our blog post about that. And certainly ring width and density don't correlate very well. They correlate a bit in softwoods like spruces, but actually in a species like oak, it goes in the other direction from what you would think. A fast-grown oak is denser than a slow-grown oak. So actually, if you're really serious about oak production, you encourage your trees to grow fast. But the main thing is that density doesn't correlate at all with strength when you're looking at individual species. Denser species tend to be stronger, but within a species, a denser piece is not likely to be stronger than a less dense piece. This is spruce, but you will see in many other species even less of a correlation than this. Density on this axis and bending strength on that axis. I wish it were that simple, but it isn't. My life would be a lot easier if it was so simple, and we could just weigh it and be fine. So how do we do the strength grading? Well, we try and find something that is predictive of the strength that we can measure non-destructively, and then we set a limit on that, and we try and sort out the stuff that is less strong. What we're trying to do is find out information about the tail, about the low end, because that's where bad things happen. It's the probability of having a low strength piece. So strength grading is not about the mean, it's not about the high end, it's about making sure that we can manage this low end. Now this is just a random numbers from a normal distribution. And I think there's about 500 dots there. And you can see how much this jumps around with 500 dots. This is the level of randomness, statistical randomness that's in there. And I'm showing it as an illustration of how much timber you have to test to get a good idea of what the properties are. Just to put some of the figures that we might be showing soon into context, because you can't tell from doing 1 or 2 tests. You can't tell. You have to test a lot. Now, because building safety is important, we have a very complicated legal and standard system around it. I will not go into the details, but we have European standards and British standards that are all to do with making sure that the timber is safe. Now, these have grown up around our mainstream commercial species like spruce and pine and fir, and they require a lot of testing because they consider building safety to be important, and it's fine and it's correct for big buildings. But if you're doing a small building, you don't need so much confidence in the value as you would if it was a hospital. Yeah? So it's a bit OTT. It's over the top for a lot of the things that we actually want to do with hardwoods. A single-story building in hardwood does not need to be designed to the same level of certainty as a bridge with vehicles over. If you want to know what we can do in the UK, there is a paper that I can recommend. But essentially, there is hardly anything that we can do with hardwoods right now. It's just oak and sweet chestnut we have current grading route for. So now I hand over to my colleague Marlena, who will tell you a bit more.
Thanks, Dan. From this introduction about basic properties, basic wood terms, we are going back into the project. And since we are talking about building from England's woodlands, let's look at England's woodlands. Or actually here you see the distribution of UK woodlands, and you see that it's pretty much split in half between conifers and the broadleafs. In England, we actually have much more broadleafs. We have 74% of the forest cover that's broadleafs. But the timber we produce is mostly softwood. UK timber, we produce 13 times more softwood than hardwood. So where does this discrepancy come from? Why do we not make use of our hardwood resources? This is actually mostly historically grown. So in the UK, we've always been short on timber supply. And especially after the World Wars, we've needed to grow timber quickly. And that's why we planted plantations that can produce timber quite quickly, quite reliably. And these are still supplying most of our timber needs, these conifer plantations supplying softwood. On the other hand, you have the broadleaf forests, and they fell out of management during this historic period when we wanted to produce more timber. The hardwood forests are a bit slower to produce timber, need to grow longer, and then talked a bit about that. So these fell out of management, and they were also kind of perceived as a counter-approach to the plantation forests. Owners had other objectives, not necessarily timber production, but they wanted to grow forests that they like to be in or that are good for the environment, that people like. And they thought maybe that leaving forests completely alone was the way to do that. Still, these other objectives, other functions of the forest are of course very important. So we started planting more broadleaf trees since the 80s. And at the same time, since then, we also recognize that forests are not necessarily either or. They cannot really be either productive or good for the environment and good for people. So nowadays, these functions of the forests are all coming together. And that means we will probably have more unusual timber resources to deal with in the future. So on the one hand, from our productive conifer plantations, we might be getting some other species than the ones we are used to. Not only do you need to comply with the UK Woodland Assurance Standard, if you want to make use of grant funding, and this standard says that you cannot have more than 90% of one species. You need to have at least 10% of another species. So people are planting some hardwoods in their conifer plantations. But not only that, people are also recognizing that really mixed forest does give the forest other benefits. It makes it more resilient against pests and diseases, and maybe also against climate events. So we might have more mixed productive forests in the future. And of course, if foresters can make use of this resource and bring it into their crop, then they would be very happy to make money also from these other resources that could be hardwoods. On the other hand, in the broadleaf forests might be coming also back into management, at least for some timber production, because obviously forests need to be sustainable also financially, and people are recognizing that not managing the forest is not necessarily the best for the environment or for other benefits of the forest. So we might have a variety of resources come from these forests in the future, and that might be storm-blown timber, that might be coppices, that might be park and straight trees as well. And we need to deal with all these resources. And the more unusual and various resources we have, the more we need to deal with uncertainty and variation in our timber. But we do want to use this timber, not only because we think that it makes sense, but also because our softwood supply is actually going to decline from around 2030 already. And our timber consumption is not going to decline. So it would be really nice if we could plug this gap with some other resources, and hardwoods at the same time will become slightly more available. And this is a forecast that is now nearly 10 years old, so maybe there will be even more hardwoods available than here, forecasted here, for all the reasons that I just mentioned. So yeah, it would be really nice to make use of these hardwood resources for the same uses that we use softwoods for, which is a lot of fencing and packaging, where we don't necessarily have that much demand to timber quality. But surely we need to know about properties also for these uses. But there's a lot of construction timber, and for construction timber, obviously, we need to know a lot about the structural properties that Dan just mentioned. If we wanted to use hardwoods for these purposes, we would need to do something differently than we do now, because at the moment we are burning 85% of the hardwood we harvest. That is, for many reasons, but one of them is because we don't know all that much about UK hardwoods. So if you asked us about any mechanical properties of anything that we have displayed on our little hardwood table, we can't give you an answer, because there's very little research on that. So there was some research in the 1930s to 60s, but that was mostly on small specimens, mostly on a handful of trees, a handful of specimens, and that's all the data that we have on most UK hardwood species. And this is why we are doing this project, so to learn more about the properties and specifically this work package. And Dan is going to show you how we do this a little bit.
We'll just give you a taste of it. So we're going to play a game. But before we play the game, just to summarize what Marlene said there. So we've got certain motivations for looking at hardwoods. One of the motivations is that society needs wood. In fact, wood demand worldwide is probably going to triple or quadruple. We're very hungry for wood, and it provides a lot of things that are very important to basic quality of life. I'm sure since the pandemic, we all know that things like toilet paper, when you don't have it, suddenly a product that you don't really think about makes a big difference. Well, there's a lot of things that wood provides that are like that, and if they disappeared, we would really notice them. And so that's one thing, is that we think that we're going to need a lot more wood. The other thing is that we are putting a lot of pressure on certain types of forest to provide all of that need. And we need to relieve the pressure from some of those resources, because it's very bad for the ecology of those forests. The other reason is that we do need to move away from this quite limited diet of tree species that are providing our timber needs. And that's very important for that existing timber supply because of the risks of pests and diseases and so on, just coming along and decimating everything and killing the industry. So we need to think about how we would diversify the kind of timber that we work with. And we are just talking about hardwoods today, but a lot of the things that we're saying also applies to the lesser used and emerging softwoods too. It's the same kind of technical problem. And the other thing is that we need to think about everything else in the world apart from us. And we want forests to be in a certain way. And in the past, we would say, well, we want wood of a certain type, so let's bend the natural environment to provide that. But rather, we should maybe think about what kind of forest do we want to have in the country, and then think about what kind of product they could provide. So we're not necessarily talking about going back to the kind of forest management we had with hardwoods in the past. It might be a different kind, but it's all about thinking about what those hardwood forests can provide that will provide an income for the management of that forest, which is good, provide a contribution to the material needs of society, which is good, and also would relieve the pressure on the softwood forests that are degrading certain things that we should care about. So that all sounds good, but how the hell do we do it? Well, getting the strength of wood is not as easy as it sounds, and it sounds hard. So it's even more harder than that. So we're going to play a little game just to give you a taste of the kind of thing that we're doing and just to show examples of the kind of work that, the kind of science that we do back in the lab. I'm going to show you an EN 408 bending test. It's the standard kind of test that we use for construction timber. It's 4-point bending for reasons. But essentially, we have 2 points of support and 2 points of load. And in the middle there, we have pure bending. Pure bending. In the outer part, we have bending and shear. But this is a bending test, so we want it to fail in the middle. Of course, there are other things going on that I've already talked about. We have compression here, where the support is. We have compression here, perpendicular to the ground under the load. But this test is designed so that it fails in bending, because that's the property that we want to measure. Now, I'm going to show you 4 beams. And then I'm going to ask you questions about your predictions for those 4 beams. So concentrate, concentrate. The first beam is the first of 2 beams of oak that we have. This oak has a little bit of grain deviation here. I'll zoom in a moment to show you it better. But this was an injury on the living tree. It's a wandering pith. There's also something that looks a bit like a knot. We're not quite sure what it is. So let's zoom in. There, a bit of slope of grain there, and just about visible is a knot. Now, this is one example of actually how difficult it can be to observe defects in wood in real situations. So if you're air drying hardwood, often it will get dirty like this, so you don't have a nice clean surface to be able to see things that you would normally consider to be diagnostic. So that's the first oak, as something that we might consider to be a defect. The second oak does not have such deviation in the grain. It's nice and straight, and there is nothing that looks like a knot. So a nice, straight bit of oak. So they're your 2 pieces of oak. Next one is ash. Nice, clean piece of ash. Well, there's dirt on the surface, but there's no visible defects, I think, in this piece of ash. It was reasonably straight-grained and no knots. And the fourth one is sycamore. Bit of an oddball compared to the other 2 more mainstream species, but a nice piece of sycamore with no defects, nice straight grain as well. So, your predictions, please. Which of those will be the strongest? Hands up for oak 1. Steve knows how this game works. Hands up for oak 2. Yeah, quite a lot of votes for oak 2. What about the ash? Oh, ash fans, yeah. And sycamore. Yeah, okay. Bit of disagreement. We'll see. This was all randomly chosen, by the way. It's just dependent on what we had videos of. So no funny business here. No tricks. No tricks. So which will be the weakest? Who says oak 1? The oak with the defect. A few votes for oak 1. Oak 2, the nice straight piece of oak. Well, Rory, brave. Ash. A few people think ash. And the sycamore. Right, so guaranteed that some people are going to be right. So which will be the stiffest? So stiffest. So least amount of movement for a load, or most amount of load for a movement. So when we look at the graph, it will be the one with the steepest line. The steepest line. So which will be the stiffest? Votes for oak 1? Yeah, votes for oak 2? Votes for the ash? Votes for the sycamore? Remember what you vote for. Just don't vote back randomly. Right. Okay, different kind of question now. So which one will bend the most? So which one will I be able to deflect in the most in terms of millimeters before it breaks? Oak 1. Votes. No one. Oak 2. Yeah, 1 vote. Ash. Few votes for ash. People know ash. Sycamore. Okay, few votes for sycamore. Right. Okay, will they all be stronger than British spruce? Just a yes/no question, simple. Don't know why you're laughing. Simple question. Will they all be stronger than British spruce, typically? Votes for yes?
I think it's the spruce.
Same size, right? Yeah, everything is the same dimension. Who says yes? They will all be stronger than British spruce. Okay, and will they all be stiffer than British spruce? Yes, votes? Few? No votes? Few, yeah, okay. Time to play the game then. Right, so you're going to see a graph develop. I'll bring it up on the screen. We have on the x-axis the crosshead movement. So that's how much the machine is pushing down. So this is effectively a measure of the deflection of the center of the beam, an indication of the deflection of the center. On the y-axis, we have the force. We measure in science units, kilonewtons, but I have translated into real human units. So 10 kilonewtons is about a ton's worth of force, and 20 is about 2 tons worth of force. This is where we would expect to find British spruce within this range. So 5% of British spruce species will be stiffer than this, and 5% will be less stiff, but we would expect the vast majority to be in this grey zone here. So if you thought that all of the pieces will be stiffer than spruce, you would expect their lines to be on this side. If they're in here, they're as stiff as spruce, and if they're below, they're less stiff. Right? And this is the strength. So strength will be the one that reaches the highest on this axis. So ready to play the game? No questions about how this is going to go? Make a bet with your neighbor. Feel free to exchange money. Okay, so the first bit of the test is speeded up 10 times, just because life is short. So we can already see that we have one which is much stiffer than the others. That's oak 1. Oak 1 is the stiffer one. That's the one with the defects. Oak 2 is the next stiff. And then ash and sycamore are both more or less equally stiff. And they're about as stiff as the stiffest kind of British spruce. So they're not necessarily all stiffer than British spruce. Right, slowed down now because it's into the time where things might happen. So already oak is winning on the strength side, but, you know, others might catch up. I just checked the video is still playing, yes. This is the speed at which the test normally progresses in real life. Can you hear? Something's cracking. Oh, oak 1's gone. Well, so far it is the strongest, and it's already we know it's the stiffest one. So that went in a quite nice way. There was a certain amount of predictability of that failure. We heard some cracking. So if that was in a real building, we might know there's a serious problem and we might have time to leave. So that was quite good. Sort of behavior that we like. Okay, so which one's going to go next? At this point, they have bent quite a lot. It's hard to see in the video, especially when they're playing slow. But you can bend wood quite a lot before it breaks. I mean, if this was a beam in your building, you wouldn't. At this point, you would know something is wrong. Oh, what's gone? It was the sycamore. Now watch this. Pretty brittle, explosive behavior. I don't know whether that's typical of sycamore overall, but of the sycamore that we've tested, it does tend to go like that. That's probably something to do with growth stresses in the living tree. That's not a kind of failure that we would like to have in a real-world situation, because there's not much warning, and suddenly it's into several different bits, and your beam's gone completely. So, oak 2 and ash still in the game. Something is creaking. That's the oak gone. Right, so oak 2, which was the cleaner looking one, was actually less strong than the one that had the wavy grain and knot. And now ash. And I might speed this up, because ash just hangs in there forever. Can I speed it up? I don't know if I can. I have to go over here. Oh, it's because I'm on the laser. Oh, I've broken it. We have to watch this whole thing again. I hope not. Oops. Expert. Yes.
The 90% of British spruce, are you referring to basically the C24 stuff in Scotland, whereas the 10% is all the weaker bits in various parts of England?
That might take us as long as the video plays to answer that one. This is ungraded spruce. So this is the spruce resource overall, which would typically be graded to C16. So in this country, almost everyone is grading spruce just to C16. And I'll show a slide in a moment explaining a bit why that is. Literally can't grab that playhead thing. Anyway, the ash goes on and on and on. Take my word for it. You'll see it actually in the break. And that's a kind of stereotypical property of ash. Actually, that's one of the reasons why it's favoured for handles, tool handles, because it's reasonably strong and flexible, but you have to bend it a lot before it breaks. So quite good, actually, for building safety, that kind of behaviour. Now the nerdy stuff. For those people that do understand timber grading, everyone else can tune out here. But I have a complicated graph here. When we're strength grading, we have to basically satisfy three different things: strength, stiffness, density, these axes. And I've scaled this so that British spruce is a perfectly equal triangle, so that I can compare birch to spruce. And we have certain targets for the strength classes. And British spruce meets very well the requirements for C16. In fact, I could say that the other way round, really, because C16 was invented to match the properties of spruce. Because the strength classes don't come from space, they actually correspond to the properties of the real-world material. So it fits pretty well to C16. There's actually a little bit of extra strength and a little bit of extra density, which is what C16 plus is about. It allows you in certain circumstances to take advantage of those extra properties. But for these odd species, the situation is much worse. We have a much poorer match between the strength class definition and actual properties of the timber. That's because these strength classes that exist for hardwoods are designed for the relatively dense mainstream traditional hardwood species that we'd be using in construction, like oak and beech. So if you have something like birch, which is denser than a lot of people expect it to be, but isn't as dense as beech and oak, it's actually limited to the strength class because of its relatively low density, and it has much higher stiffness than the strength class has. So when you're grading it, you're actually throwing away a lot of the potential of the material just because of the definition of the strength class that doesn't fit very well. Actually, now you can put a hardwood into a softwood strength class, which would certainly make sense for hardwoods that are a lot like softwoods, like poplar, for example. But even if you did that, you're still sort of throwing away some of the potential. So the reason I show this is really to say that we're not just doing research on the wood properties, but we're actually trying to do research as well which will support some change in the actual standards, so that we can change the standards so that they're a bit more compatible for using a more diverse resource. And this is not just a UK problem. Everyone in Europe is facing this problem. They want to have a wider range of species coming onto markets, things like sweet chestnut, that don't fit very well to either a C class or a D class in the system. And so that's it. I will hand you back over to Marlena. We're not finished.
No, not finished. Whoops.
We might have enough, but we're not ready.
We're getting there. Yeah, now we have already seen 3 species that we are looking at in the project, and let's just talk about hardwood species and which ones might be interesting, which ones are we working with at the moment. Does this work? Here you have a little overview of the hardwood species growing in the UK, and right away you can see that we have a bit of a mix. There's not any one species that dominates the forests, like we have with softwoods. 50% of what we are growing is Sitka spruce. In hardwoods, that's different. These are the 10 most common species in the forest, and in the end, you see there's a lot of other species. So many of these might have potential, and many people might want to use some of these species, all of these species. And we kind of needed to make a choice. What do we look at first? These are the 10 most common species, and we thought we might look at most of them. Right from the beginning, we excluded hazel and hawthorn just because of how they grow, and we didn't think they would have much relevance to sawn timber. Might be relevant for other products, coppices, or what do I know. But we wanted to focus on these species, and for our first kind of really overview look into properties, we went to a sawmill and we wanted to buy boards from all these species. They couldn't supply birch, willow, and alder. So we bought these other species. But as Dan said, we wanted a mix of species that are more like hardwoods and species that are less like hardwoods. And I will say a little bit more about that soon. And so we also bought poplar. And these 6 species, we have basically finished our first round of testing now, and we have brought them along as well, so you can have a little look at these 6 species later on. The species mix, yes. We have some hardwoods in there that are a lot like traditional hardwoods, and that's sweet chestnut and oak. These are like traditional hardwoods in the sense that we have been using them for building, and these can be strength graded just because we know that we have been using them in buildings, not because we have tested them and know a lot about the properties. So the strength class assignment of these 2 species is based on long-standing traditional use. And in this project, we can look a bit more into the mechanical properties and see if that actually makes sense, if we are assigning them to strength classes that actually match their properties. Then we have some other species like maybe birch, ash, beech, sycamore in a sense. We will see if that actually is true, that might behave more like hardwoods than softwoods. So they might fit into this triangle of our strength class definitions quite well. We hope that if we would assign them to hardwood strength classes, we would not waste a lot of their potential. And we also hope that we can calculate secondary properties that you would not normally measure in your strength grading assignment, that you can calculate with the equations that are given in the standard for hardwood, which are different from equations that you would use on softwoods. So we will do some testing on secondary properties like hardness, compression, strength, and so on, and see if you calculate the same properties from your strength, stiffness, density, if that we get to roughly the same, or at least if we are on the safe side with these equations. And then we have some species that are lower density, and they might behave more like softwoods in these same terms than hardwoods. So we might want to assign them to softwood strength classes, and again, we need to look at, do they fit in our triangle of strength, stiffness, density, or do we maybe need to do completely different things if we want to strength grade these? That's the species we are looking at, and when I say looking at, I will go a bit more into what we're actually doing. So first, of course, we need to sample our wood, and that's a whole thing of itself, because you really need to get a representative sample of what you're growing to do the properties characterization. Because wood is so variable and all the growth conditions affect your timber properties, and that's climate as well as forest management, you need to sample trees that are grown in kind of typical conditions, and then you need to saw them in a typical way to get a typical piece of timber out of that. And just this month, we had the chance to actually sample some trees. So we could select them to get a range of properties in our timber sample. We could measure some diameters, some heights, and we had a proxy for quality. We did a dynamic stiffness measurement, and hope that this will give us some information about if the wood in the tree is stiffer or less stiff. So we are trying to sample the whole quality range. If in many cases, here's some more pictures of that. In many cases, we can't really sample trees, but we have to buy timber from sawmills. And in that case, we just hope that the sawmills are felling typical trees and are processing the timber in typical ways and are giving us all timber of all qualities. So we tell them to not sort it in any way, to give us the timber with all the defects, everything that they would normally sell, in a way sawn and dried and processed as they would normally do. And that's the best way we have at the moment to get typical timber. And then we do different tests. So in this research, we do the bending tests, just as you saw in the videos. This is what we would normally do for a strength class assignment, only the bending test to get bending, strength, stiffness, and density. Then in our research, we also do characterize secondary properties. Here, on small specimens mostly, you do things like compression tests. Here, this is a hardness test. What else do we do? Shear strength, things like this. So these you would normally not measure in your strength grading assignment. You would just calculate that from an equation that is written in the standard. But we want to see if these equations actually work, so we are doing the testing. And then we're doing some non-destructive tests. The last test here is a torsion test. It doesn't look like it's non-destructive, but the machine just twists the timber to a point that it doesn't do any damage to the timber. So that's one non-destructive measurement. We also do, of course, acoustic measurements, dynamic MOE, things like this. And these non-destructive measurements can then hopefully be used to predict the properties of timber that you actually still want to use. So that's obviously a big part of strength grading, to relate your strength, stiffness, density to non-destructive tests. That's what we are doing in the lab on all these different species, but there's probably a big part of using hardwoods that is not necessarily related to mechanical properties. So as we have touched on, processing hardwoods is a bit of effort. Grading hardwoods will be a bit of effort because we cannot in this project test enough timber to just then send it through a machine, put a stamp on, and you can use it in your building. But we can maybe provide ways that people can use hardwoods if they are willing to put in this extra effort. The question is, why would they do that? maybe hardwoods are just nicer to look at, or maybe you want to use the ash that is grown in your backyard or things like that. But these are factors that we cannot quantify in the lab. So I'm asking you, if you have a bit of time in your break, to look at our wood cubes over there, little cubes like this. And if you have any kind of association with that, do you like it, you don't like it, you like how it smells or tastes, grab a pen, write it on there, give us some ideas what you would do with these hardwood species and why you would be willing to pay money for that. Yeah, that's a kind of question that we have for you.
Obviously, what we've done in the first half of this, which Dan and Marlene really demonstrated, was really taking it from understanding of timber through the different species that we're looking at, and how we need to consider those in terms of construction delivery and all the other aspects that were fielded through the questions in terms of even climate resilience and long-term durability and so on. And then there was things getting picked up as well in terms of alternative mass timber products such as Brettstaff or dowel laminated timber. So with that, I think that really sets the scene really, really well and nicely. And what I'll do now is I'll hand over to my colleague Wojciech and team, and Paula and Finn from dRMM to explain the next work package, which starts to look at the engineered timber products in more focus, right?
Okay.
Okay, cheers.
Well, thank you, Robert. I just want to say that if I knew Dan will show some videos, I will prepare some of my own. And trust me, the stuff I test is much more exciting. We need much more force to break CLT and glue them. But anyway, I guess something I will prepare for the next time. Right, so welcome to session 2. We estimate that the presentation part should take about half an hour, and here are speakers today. So that's myself. I'm a structural timber design and analysis consultant at Edinburgh Napier University. For the last 5 years, a large amount of research I've carried out was around mass timber systems, particularly from a homegrown resource. We also have Paula Seminara, our research support, and Finn Charlson, architect from dRMM. So I said the presentation should take about half an hour. We're going to cover these 5 topics. I will start off with describing what engineered wood products actually are, for those of you who don't know or are still not sure what they actually are. And we'll very briefly outline the objectives of our work package within this bigger project. After that, Finn will take over and talk about opportunities for English woodland. And then I will, again, describe some of the research methods and ideas that we want to explore within this project. And there will be a limited time for question and answers. So yeah, I will try to come back to some of the questions that's been raised in the previous session. I'll try to address those because I might have some answers. And we will finish off with some market analysis presentation that Paula will deliver, and workshop at the end for starting at 3:15, lasting for an hour. So we would like your input and discussion, helpful discussion, because we know how to do things, but yeah, it's always useful to reach out and ask for advice and ideas, something we might have missed. Okay, timber is a great building product. I think most of you agree, otherwise probably wouldn't be here. However, timber comes with one major problem. Problem that is its biggest advantage as well. It's a natural building material, right? And a tree can only grow as high, as wide. And this significantly reduces scope of applications. So obviously, you can use sawn timber for many, many applications, been shown hundreds of years until now. However, as timber is capable of much more than just, 4-meter spans and 240 millimeters width. And that's where engineered wood products comes in. So those are the limitations I just described, the maximum cross-section size and lengths. Obviously, availability might be an issue, and presence of naturally occurring defects. This is the standing trees. Obviously, it's a living organism that needs harvest energy from the sun. That's why they have branches. Branches means knots. not necessarily what we want to see as a structural engineers, but again, natural building material. We have to deal with it. And that's where engineered wood products come in. So over the years, architects and engineers try to come up with the ways to overcome the limitations of sawn timber by the ways of combining smaller pieces of wood together. So as simple as it is, that's what it is. But those small pieces might be planks, like boards of wood, chips, veneers, etc. And if you do that, you might end up with much larger timber element that is still capable of carrying out all the loads. But also, in terms of sheets, you might want to have something which is wide by thin. So that's where all the OSBs and plywoods come in. In general terms, all this engineered products, wood-based engineered products made by combining small timbers are referred to as engineered wood products. And when you do that, the only, you can achieve any form and shapes. There are very little limitations, and those limitations are often associated with the capacity of the production plant and transportation. So this is the only limit. Naturally occurring defects are often removed during manufacture, and product tend to be much more dimensionally stable due to the fact that the logs the boards are very often dried before the production of engineered wood product begins. Obviously, I've done a lot of reading actually, on mass timber. I came with many different kind of split and groups, and how can we group different types of engineered wood product, because it's a wide area. So I generally adopt this structure. So engineered wood products generally could be divided within those three groups: mass timber or solid laminate timber systems. This is where boards or planks of wood are joined together in certain ways. So in terms of glue lamp, parallel to the grain, stacked up. In terms of cross-laminated timber, boards are stacked together in a cross orientation. So generally, you end up with large element. I think double lam also comes in this category, and laminated veneer lumber. This is just few. This is this is area of engineering when it's like really again many possibilities, right? But this is generally the four we tend to focus our attention on. Another one in the group, another group of engineered wood products that I tend to refer to as wood-based panels. This is the thin, wide, and long sheets of material. And within this group, we can distinguish oriented stand boards, OSBs, plywoods, particle boards, chipboards, just to name the few. And structural assembly, I think this is the most controversial one. Some of you might not agree, but I call it structural assembly. So basically what happens is that you take your timber boards and you join it together to create a product. So the example here is thin web joists or roof trusses. Last but not least are the other types of wood products, the modified wood. So this is where you're dealing with densification. So you're compressing timber, increasing in density. Acetylation, so when you chemically modify the molecular structure of the wood, and thermal modification. Finally, there's also a wood fiber insulation as well within this group. Okay, so I will briefly now try to describe where all those products kind of fit in within just the dwelling. I know probably mass timber is not the best example here, but this is what we have here is a normal timber frame house. Three bedrooms, 2-story house. Generally, in a lot of cases, many cases, those are constructed with sawn timber because, that's enough. However, for load-bearing elements. However, so in some cases, when larger spans are required, we're dealing with larger stresses, or it's just, we want to create a more efficient system, we might implement these products. In case of rafters, we can replace the sawn timber with I-joist or thin web posi joist. Sheathing. So timber frame have to be sheathed to become rigid, to become like the diaphragm, creating a load-bearing system. And this is where the OSB and plywood are often used to create this rigidity. In Scotland, often we use plywood or OSB for roofs as well. I think here you can also use bracing, since it's the same principle. You can use bracing or sarking, sheathing on roofs. Lintels, so this is, again, the area where you're dealing with increased load. So you've got you opening under the window, or, yeah, imagine the window would be larger. You got joists landing on this beam, and you need stronger beams. So this is, if that's the case, you might use LVL or glulam. Same with the trimmer joist. Like with trimmer joist first. Again, opening board for the staircases. They tend to take more load than just the regular I-joist, floor joist. And I couldn't miss the floorboards. They're probably one of the most popular and the one that everyone knew. So if you ever converted your attic or ripped the carpet in your house, you've probably seen one of those products underneath. So this is what is often used for flooring as to create a kind of even a smooth surface in the houses. And floor joists, yeah, I mean, yeah, they call it thin web joists, so I left them to the very end. Yeah, you can use I-joist or posi joist. In terms of the construction techniques, again, I'm going to go very quickly through them. Most of you might be familiar with it. So there's several ways you can build houses, right? So traditional method, on-site construction, when team of builders come on site with the material, putting everything together on site, and yeah, building the building up. This requires quite a lot of effort. So with the recent years, this system was optimized in what we call panelized construction, off-site construction, where the ready elements are prefabricated off-site and transported on-site. Requires less people, less operators, and houses are generally built faster. There are two types of panelized construction: open panel construction and closed panel construction, or mass timber. This is really the difference. Only here is that with the open panels, you've got only load-bearing elements, no insulation. With the closed panel panelized construction, you've got insulation and internal lining included. Volumetric construction, I'm sure you've seen fancy photos, and there is more in this presentation, so I'm not going to take too much time. So there's a way full units are constructed in factory, in a controlled environment, transported on site, lifted in position. There's also post and beam. This is probably the most appropriate when it comes to mass timber construction. Typical cross-section of the wall. Don't worry, I'm not going to go through all that. This is slides from the lecture I'm delivering at Napier. I just want to show you how typical timber frame house is built. So just to go through that very quickly, on the outside, we've got the brick cladding. This cladding could be replaced by timber cladding or metal cladding. This is some sort of shield that shields the building from the external elements. Following that, you usually have a ventilated gap with another secondary defense mechanism by means of membrane. So waterproof membrane. Sheathing, OSB usually, could be plywood, and then you've got the load-bearing timber frame elements. Followed by, one of the most important, the insulation. So that's where the insulation usually goes, in between the studs. And to meet more strict thermal regulation, you might add another layer of insulation in front. And it's finished off with plasterboard at the end. So this is the same cross-section, but simplified version of what you see here. But yeah, you can also replace the load-bearing system with the likes of CLT or another wood-based product, such as I-joist. And I know for a fact, I've seen it myself, both systems are actually in use currently, even the I-joist. Okay, so that was the kind of background information. Now coming back to the building from English Woodland project that Dan described. As Dan said, the main aim of the project is to enhance the utilization of English woodland resource for the built environment. So as Dan and Marlene are researching the kind of structural properties of the species and what grades can be achieved, what properties they will have, and the general characteristics of the sawn timber, we carry out our part of research concurrently with this team, but our focus is on engineered wood products. So how these hardwoods can fit into potentially using them to manufacture engineered wood products. It's not that simple as it sounds, which I will show in the following slides, but before that happens, I will hand over to Finn, who will introduce the project a little more. Thank you.
Thank you all, and hi. Yeah, as Wojciech said, I'll kind of situate the project a bit more within the research question, see how we're appraising some of these different systems, engineered wood products, trying to kind of look at their compatibility for the standing and kind of felled resource that we're projected to have in England, and that is England specifically, not the UK, because that's the kind of remit of the research question. But if you stand back, there's really kind of just a huge missed opportunity that we're looking at, whereby globally everything in grey is somewhere that's conducive to forest cover and thus timber production, and in everything in black is where that's actually happening. So in Norway, for example, the only places where it's not happening is where it's too mountainous. And obviously we know that places like Austria, France and Sweden, that's really happening. So we're just not really pulling our weight in that respect when it comes to forest cover, and also in turn to utilization. So there's obviously a lot of forests that we know and like, just as places that we spend our weekends and holidays, but there are in fact some productive woodlands, and you should look to Forestry Commission Forest Research for some useful information on that. But obviously a great deal of the woodlands where the timber's coming from is not in fact managed by them, but all kinds of private landholders through this kind of long and complex web of holdings and leases. But essentially this is kind of the graph that's been shown a little bit earlier that gets us as a project team excited about hardwoods and construction, because there is, from the Forestry Commission, there is a projected increase in availability, and then we've been looking at those specific species on that basis, and in particular some of them that we know there should be a little bit more of. So Marlene had explained a little bit about that, about what their characteristics are, what their properties are, and how much they are prevalent in the woodlands. And so then that's kind of something that we can directly then map onto a graphic and imagine that, well, we would hope to find a supply chain for birch, oak, ash, sycamore, beech, because these will all in themselves form quite a good chunk of material going forward. So if we go through the steps of that, what you might find is that you end up first with a great deal of roundwood logs, which already you can in fact build with. We've done this in our studio, dRMM, built with roundwood larch poles in order to develop an auditorium structure, and it's done on an experimental basis as well in some academies. And then from there you've got these kind of main processes which would need to happen. And if we're talking about having a realistic homegrown supply chain, you need to have, at least one or two of those in place. So sawn timber, that's happening. There are sawmills up and down the country, tiny ones to, well, probably only a small handful of large ones. But then there's also, you can make products from veneers, rotary cut veneers. That's something that's not likely to happen, because I think the last one closed in England 2007. And then, but there is in the UK a base for stranding and producing fibres, and obviously pulping timber within some facilities. And if you read from left to right, essentially what you're talking about is, how much of those initial properties, or should we say of the broad gamut of those initial properties that Marlene and Dan are talking about, are you able to transfer directly into the product? Because if you've just pulped the paper, then pulped the wood, then perhaps those bending tests don't become quite as relevant. So sawn timber, veneers, strands, fibres and pulp, and they can all be used to make all manner of products, these panel products. We've got some engineered wood products here as well. I'm aware that some people might not be totally familiar with them, so you can go and pick them up and interact. But essentially it looks like, you know, there is already some manufacturing base for OSB makes its way into houses from large house builders, and there is some manufacturing base for MDF. But as I say, things like plywood and blockboard, that would be a really, really big mountain to climb to try and get that manufacturing base up and running with an English hardwood. So perhaps there's some pressure points that you can kind of jump into there. Yeah, as we said, these kind of panel products, which can be used as super versatile finishing materials, generally internally. All kinds of acoustic treatments, fire treatments are readily applied, and fantastic innovations happening with the treatment of those products. Beam and joist systems, we're obviously aware that there's sawn timber just as it is, but we're interested in adding value to the homegrown supply. So we're looking very much at thermal modification to improve the performance, or indeed other forms of modification. And yeah, crucially, systems like glue laminated timber. There's some appetite for the manufacture of those composite eye joists already here in the country, but something like laminated veneer lumber might not be necessarily the right product, because you have to have huge investment in a supply chain to be able to get something like that going. Yeah, as we said, wood can be densified, improved by acids and thermal modification. We've done a couple of projects where we've used thermally modified timber. The cladding to the outside of Maggie's Oldham is poplar or tulip wood, and there's a sample down there. You'll feel it's a lot lighter. The colour becomes a little bit darker after the fact. Glue laminated timber, and then our colleagues over at BEST have been able to develop some homegrown spruce glue lam up there in Scotland, and it's also in the example of somewhere like the Sky Health and Fitness Centre. It's not really as straightforward as this post and beam construction, but you kind of look at the whole suite of mass timber products, understand what might be the best application for that time and place. And again, you can still read that increased processing as you go from some kind of readily useful, but should we say kind of more less, shall we say, innovative or versatile systems in decking and flooring, commonplace trusses, and so we're seeing definitely potential for mass timber products developed from English hardwoods, which is something that Wojciech can elaborate a little bit on. But for those who maybe aren't aware, something like a SIP is growing in interest, which is essentially a kind of insulation sandwich with OSB. There are some great innovations in terms of these kind of lattice panel constructions to try and minimize the amount of material that goes into the mass timber product. And then this opportunity is definitely for dowel and nail laminated timber. Just to kind of put that in context, you might find that with CLT, for example, a project that we developed some years ago now, the Naked House, tapped into this. Not only with that product are you looking at a different performance in terms of the fundamental product, in terms of thickness, density, strength, but the opportunities and kind of the tooling processes that necessitate its production, so that here there was where you'd had a hole cut for a skylight that then became a table, where the door opening became the entryway, and then the windows became the shelves. I thought it was important to also talk a little bit about prefabricated systems, because here, obviously, in the UK, you're not exactly looking at kind of trying to compete with some raw product manufacturing with massively cheaper overseas competitors, but actually there's already a history of adding a lot of value in terms of the kind of later stages of product development, in terms of the advanced information technology that you need to develop some of the prefabricated systems, ability to coordinate high levels of information and to improve the performance characteristics through panelized prefabrication. We heard about some of the good stuff happening with closed and open panel construction there, volumetric, and then we're seeing some really interesting modular cassette systems emerging as well. We've got a project just wrapped up on site down in Charlton, which is not modular in the not modular and volumetric in the sense that so work stack building up on the right, in the sense that you're transporting air through a large module, although in many situations that's extremely appropriate solution to, say, a remote location or what have you, where you simply can't be working on site. But work stack is this idea that with cross-laminated timber, with mass timber, you can just make enormous program savings by delivering flat panels to the site, and currently they have to all come from Austria and Scandinavia, but if that could happen closer to home, then you'd end up with a really, really efficient construction system. So yeah, this is what we're looking at in England. Essentially, you've got this large number of red dots of sawmills who are just trying to kind of make a living from adding a bit of value to what is already quite considered a low value product. And then you've got also then, you know, a number of them diversifying, offering other products, other systems, trying to become a bit more integrated. And you've got a very small number of engineered wood product manufacturing facilities. So just kind of get us all excited about this potential for, you know, integrating hardwoods. As Dan and Marlene had pointed out, there are different performance characteristics, and we're not just talking about trying to, although that is a good opportunity to try and replace, for example, birch within an OSB panel. That might well be something that's worth doing, and that's perfectly scalable. But actually, there's potentially enormous opportunities with the integration of hardwood to unlock opportunities for design that just weren't there previously, and we see that happening. There's a hardwood product over there which achieves enormous strength to weight ratios, which you simply couldn't achieve with a softwood alternative with the same spans, the same depths. And then perhaps we're thinking about how the elements themselves might become a bit more tailored or a bit more advanced and improve performance with the introduction of hardwoods. We've had some experiments with this in the studio. One of our directors, Jonas Lenzer, designed this lean-to structure, a pull-tool frame, whereby a hardwood multi-species lamination massively improves the strength of that beam. And the idea is that the different species are then tailored to the performance requirements of that specific part of the block itself, of the structure itself. So hopefully I don't know if that timer started earlier, but here we go. Wojciech can go on and tell you about the ongoing research for the project.
Thanks, Finn. That was very useful. That was very interesting. So I remember last year, at the beginning, June 2022, okay, Wojciech, do you want to lead on work package 3 and investigate opportunities for hardwoods in engineered wood products? I say, yeah, sounds exciting, but then, okay, where do we start? It's like so many possibilities. I mean, the ideas were flowing. And then so we had this discussion, okay, so naturally in any research, the first step is the lit review. So this is the kind of methods we adopt in the research. Then are the product requirements. Obviously, engineered wood product made of hardwoods will have different requirements. The way we put them together might differ from how we put together engineered wood products made just from softwoods. And then we thought we're going to carry out the structural appraisal. However, very quickly we realized that, especially with the system that require a lot of volumes of wood, such as mass timber systems, it's not really feasible, or it is possible, but it's not feasible to utilize the hardwood throughout the entire section. So being a structural engineer myself, so I looked into stress distribution when beams are loaded. So we know where the stress is the highest and what determines the strength and stiffness of each of the panel. And we can identify those sections and maybe reinforce them with stronger material, such as hardwoods. And this is what we're going to do in terms of mass timber. So for me, this is most exciting. So there's a CLT, there's a glulam with different layers of, the species being introduced to different layers in strategic locations to best use the material. There's also a room for dowel laminated timber. I know there was a question here about dowel lam. Yes, we've carried out significant amount of research in the past. We have data, and we intend to publish it alongside with other things that we come up with. We might even add on to it, because as I said, the focus of dowel lam was on dowels, hardwood dowels, densified dowels. But that's not to say there's some nail lam in test program as well. So it's all going to be there. So if you're interested, just stay tuned. Wood-based panels. Again, it's currently many products already exist that utilize hardwoods, beech plywoods. We've got birch plywoods, and with OSB, the interviews actually were quite interesting. We've carried out several interviews, which Paula will talk more about. So, so we are going to include those in our outputs, but it's going to be kind of limited. We won't be able to test it. That's what I'm trying to say, because it will require a lot of, probably additional funding, probably sending the homegrown strands abroad or something like that. Thin web joist, something I want to look at as well. Again, hardwood flanges, see what happens structurally. So far, we've reviewed 36 research publications, 16 on hardwood mass timber, 13 on hardwood wood-based panels, 7 on hardwood wood fiber boards, and 8 on hardwood thin web joists. Well, research is still ongoing. This is not a closed list. The number will increase as we go ahead. So the idea was to learn more about mass or engineered wood products that are made of hardwoods. So there's a relatively new area for us there. There's certain things we don't know yet, so we hope to learn it from the literature and present it to our funders. So general consensus that, okay, there is a much bigger document. I try to find the kind of main things that we found out from the lit review. General consensus is that hardwood mass timber, such as CLT and glulam, actually that's a nice image, shows improved strength and reduced deflection, so increased stiffness. Also, as you can see, actually picture here, on the right-hand side, you've got a spruce glue-laminated timber, and on the left, you've got equivalent glulam made of beech. When I say equivalent, having the same stiffness according to tests carried out by the researcher, which I forgot to reference to. So the general consensus is good. However, the researchers highlighted certain aspects that we should keep an eye on. Those are associated with the production requirements and manufacturing criteria. In many cases, I mean, probably most of the engineered wood products I looked at, they all going to have certain kind of standards, harmonized standards in the way you assess them. And they have certain ways that they have to be produced. And if you do that, you've got a compliant product. And those compliance criteria are usually, in most cases, associated with the mechanical resistance, durability. This is usually taken as natural durability of wood, but within the durability, I also mean the durability of the bond between the layers. Resistance and reaction to fire, release of dangerous substances, and dimensional stability. So those are the compliance criteria, pretty much applicable to all engineered wood products that we are looking at. So as I said, from the lit review and from studying of the standards, we've kind of identified the key points that we should address when we carry out our research, because we will make prototypes, mass timber, CLT, glulam, hopefully iJoist as well. From hardwoods or just combined sections that will include hardwoods. And if we do that, we have to be careful of how we put them together to make sure the bond is best possible. So careful consideration should be given to adhesive type. Keep an eye on the dimensional stability, because hardwoods tend to be dried at a lower density, and then when the equilibrium moisture content is met, then they might kind of mess up the section a little bit. If we try to optimize the section with introducing just thinner slices of boards, that might need more processing time, and so on and so on. So this is something that we will address, report on, and provide recommendations for everyone who would like to produce engineered wood product with hardwoods. All right, emerging results. So the next step, so we've carried out this lit review. We have a good idea now. We've sourced some timber that's waiting in the storage. Next step is to put something together, start testing. So as I said at the beginning of this part of the presentation, we are not going to create glue lumps and CLTs entirely from hardwoods. We will focus on the strategic areas, usually top and bottom layers, but also in a certain particular section, so where the hardwoods can be used from structural point of view to do its best use for hardwoods. And then, yeah, so these are the layouts we're probably going to do. The idea is to create a series of design calculations. I like my Excel spreadsheets, but the thing is that I will extrapolate from that, make it amendable. So as Dan and Marlene carried out the research, I'll be able to replace generic number for any of the hardwoods with actual number that Dan and Marlene generate. And that will give us the overall performance of the given panel. And this is the kind of test I'm looking to do. This is something we've done many times in the past. So that includes bending, compression, shear, and bond strength. We will start with the bond, as this will show us idea, because I think we have 4 or 5 species now in the storage. So I will try to combine it with spruces and see what combination of adhesive, closed, open time will give us the best possible bond. Then we're going to move on, hopefully, to the large-scale tests. Before we do, though, probably going to check the finger joints, because lit review suggested that the finger-jointed hardwoods might not react exactly the same way as softwood does, so we have to look into that. However, probably the most exciting part is the glue lump. So this is directly a result of the interviews and the feedback we got from engineers and architects. Look, what if you would use glue lumps in the most stressed sections of the beam, like top and bottom layers, like where the connections are, which are usually the weakest point of the system, or to be minimalistic, just just very small parts of the beam. And the idea is to test it and see what results with what improvements we get. This is just a part of the entire test program we're looking to do. So more of it will be shown in the Transforming Timber platform. And yeah, so after all this, we still got some time to do it. I'm hoping to start testing later this year, before the winter, hopefully. The idea is to create this kind of specification sheets for every panels we've tested. So the reader who's interested would like to learn more about what we've done and what are the properties of this particular panel consisting of this particular species, will be able to refer to this kind of tables. The output from our research will also be published in the form of debriefing papers. We recently stay away from kind of creating long, lengthy, like 100-page reports which no one reads. We tend to kind of focus on now publish our results in a briefing paper format, 2,000, 3,000 words. More accessible, more approachable, more easier to read. So this all will eventually emerge and be available for you guys via the Transforming Timber platform.
Like from our point of view, there is very big space for hybrid products, because this is what there is out there, and you can use of course is a good use of material, and you don't just build just everything in hardwood, but you use the hardwood where is necessary. So we know as well that there is a CLT made full of birch, and anyway, it gives some reduction in volume. And we also know through our research that actually there is a company that's making OSB panel, and they use 30% of hardwood, and doesn't make any change during the manufacturing process, and they do purely because of biodiversity, because the access they have to the wood. So it's something that could be done potentially here in UK as well, in England. So we know that there is thermally modified wood as well for cladding. There is a company, Vasten, where they are using homegrown ash, poplar, and sycamore, and there are also joinery. Is probably like, I would say like there is like 3 different markets. Of course, from our interview, what we got is the joinery is the easiest and more like ready market is there. It just maybe needs more communication between the forestry management and, you know, the sawmill and then the production, the manufacturing. So it's missing the connection between these identities, but it's there. The products are there. Same with the thermally modified wood. It's requiring anyway less investment than what can be mass timber. That, of course, we know is something that probably is not going to happen soon. There are just few manufacturing companies here, but they are already doing anyway using local hardwood. So why don't we try to push that one a little bit further? So from the survey result, I'm going to touch very briefly, but what we get is basically that there is like one of the factors that is a barrier of using more wood product in general is a lack of skill and knowledge, and like this reflect what is being like also said by the Timber Development UK Skill Action Plan, and what we are trying to achieve as well as NMITE with their timber design, timber technology, engineering design courses. So we know there is a lack of skill there, and it's not just about doing research, but it's what we are doing now today.